So, good afternoon, ladies and gentlemen. It's a pleasure to introduce this special session on a new topic of composite design, and we hope you'll find this interesting as it's pretty new and is all about a book that is being published by JEC in combination with Professor Tsaï of Standford, a book which will be in the bookstore in JEC in June. There's some really very new stuff in here, including some parts you'll see later on, which should really arouse your interest. The topic of conversation, I guess, is double-double. It's a new perspective in the manufacture and design of composites. The book is basically a compilation of 10 chapters written by various prominent authors, which has been compiled and edited by Professor Tsaï, who will in fact be joining us by video link from the Pacific in order to give his presentation. We have 4 of the authors with us, including Professor Tsaï today, to give an overview of the concepts mentioned, and I'll be introducing the authors one by one. So, as I said, oops, what happened there? I think we've lost the slide. Could somebody please put the slide back? Thank you very much. There will, as I said, be four presentations, and the titles will be introduced in detail as we go through. I want to save time here as much as possible. So, double-double, the first presentation is going to be given by Thierry, who's the CEO of Think Composites. Thierry graduated from École Centrale in Materials Engineering and also has a PhD in Mechanics of Composite Materials from the same institute. He was assistant professor on composite materials at ENSTA in Paris Tech Engineering School. He's a World Fellow of the International Committee on Composite Materials and a visiting professor at Standford University. He and Professor Tsaï have worked together for more than 40 years. Thierry is the head of Think Composites Europe, a not-for-profit organization for the promotion of composite materials in industry. He has developed various softwares for optimum design of composite laminates, and recently he contributed with Professor Tsaï to LamSearch, a powerful tool for the design of optimum double laminates, a cutting-edge technique that will revolutionize the way to design and build composite structures in the future. So, Thierry, the floor is yours.
Thank you, Andrew, for the nice introduction. Thank you, everyone, for being here tonight at the last session. It was a little difficult. But anyway, I want to, in this very first part, to introduce you what is the content of the new book. The book will be available at the JEC bookstore, so you can get it online. It will be released under hard copy probably 1 month from now, but it's already released under an e-book copy that you can get also. This new opus of Steve, he wrote about 10 books already, but this one is really an international cooperation. That the book covers the book, very nice, and I will explain what it is, or Steve will explain what this graphic means. And when I mean international cooperation, I mean that we have, of course, people from the States, but people from Germany, from Italy, from Singapore. We have people from UK, from Portugal, Italy again, and of course France with me. So what are the main topics you can find in the book? The book is really to tell you exactly what is the foundation of this new theory about double-double. Then there is a whole chapter on manufacturing of double-double, because of course, if you know what it is and you don't know how to make it, it's no worse. And also there is a large part on homogenization, and Steve will explain you why it is so important to be able, with the double-double, to get homogenized laminates. And of course, we will show you that important work on the design how you can go from your quad that you use in tradition to a double-double with the same efficiency, but many advantages that you will show you. Then also we deal with interlaminate stresses, all the other problems you can meet, and we will show that the buckling and interlaminate stresses are under control. The notch response, and Albertino will take you into this world about the notch response of these materials. Steve also would tell you about the grid structure, what is the great news. That's another big event here to show you what we can do with the grid skin, composite skin structure. And Naresh will tell you about certification of the material for aeronautics and aerospace application. So what is a double-double? What is behind double-double? It's some very simple concept. You just take an angle ply, two orientation of fibers on a material, and we call that plus minus phi. Then you take another angle ply, plus minus psi. So you have two angle plies. So you just stack them together, and you get the building block of a double-double. The building block is a set of 4 plies, plus minus phi, plus minus psi. Phi and psi can vary from 0 to 90. So you have a continuous world of double-double. So a double-double has always 4 plies. So your pattern, your building block is always 4 plies, and you will see that this is a real advantage over any other laminate. And a DD laminate, for your use, is always built at the repetition of the end building blocks of this 4-ply system. So what is the comparison with the quad, for instance? So in the first part of the top part of my slides, you see the classical quad. The most classical is the quai, isotropic, 090 plus minus 45. Then we have shown what they call the hard laminate with more zeros, and the soft laminate with more plus or minus 45. And you know, and these are the basic 7 laminates you always find in all the aeronautic applications. Either they go quasi-isotropic, and when they need hard, it's one of them, it's unit softly one of them. But what you see is the number of ply in the building block is increasing as you go from the left to the right, where we can replace by a double-double exactly the same stiffness, exactly the same strength, but the building block is always 4 plies. So you get a very big advantage in the facility, easiness of construction of your laminate, because you have always the same pattern, and you just repeat it through your laminate. If you compare, so if we compare quads, and we advantage pro and cons for quads, quads is always difficult to design. It's not that easy. I've been doing that for many, many years when I was young, and designing good quad takes a lot of numerical skill. Manufacturing is not always easy because you need to check. How you can check and ensure that all your plies are here and in the right place. Tapering is almost a nightmare. If you want to go from a thick laminate to a thin laminate, which one do you take off? 0 plus minus 45, how you connect these together, that's the nightmare of the numerical designers. So if you compare to the advantages, you find there is no much advantages, and sometimes people just give up on the composite materials just because of this. When Airbus says sometimes, the next plane will be aluminum, this is because of quads. So if you turn to double-double, you see there is all those advantages because it's still lightweight, it's homogeneous, and that's a very important word, homogeneous, orthotropic, easy to taper, and easy to process. And suddenly, the balance goes the other way, and this comes to be the winner. Okay, this is my short introduction. Now I'd like to give the talk to Steve. Can you?
Okay, it's my honor and privilege to introduce the next speaker, Professor Tsaï. Stephen Tsaï has been active in the composites field for probably close on 70 years, which is an incredible record. He's worked for, he got his degrees at Yale, has worked for Ford Motor Company, Washington University, the US Air Force Materials Laboratory, and Stanford University. He's known for his Tsaï-Hill failure criterion, lamination parameters with Regano, the Tsaï-Wu failure criterion, and other strength ratios. The help in Tsaï micromechanics formula, trace, masterply, omni-envelopes, and unit circle failure criterion with Mello, and double-double laminates, of course, as we'll hear today. He's worked on lam search with Thierry and Shah, metallic grid, plus or minus 60 CFRP skin for glueless assembly with Xing, Wang, Kapo, and Jin. So it's my pleasure to introduce Professor Tsaï, who will be joining us by video link from the Pacific. So please connect Professor Tsaï.
Steve, are you online? Oh, good.
Yes. Thank you. Thank you very much. It's our pleasure to talk about double-double. The first slide will show the difference between the traditional laminates and that of the double-double. This is the first slide, and hopefully they will be able to show that. As you can see, the difference, there are the traditional versus the double-double. Traditional on the left, where you have fixed angles, so 0-90 plus or minus 45, but variable thickness from 12 to 32. Whereas double-double on the other side has a variable angles from 0 to 90 and fixed thickness, always 4 plies, as Thierry just mentioned. So when you have only 4 plies, then you do not have to make the laminate symmetric, because you can homogenize the laminate by using a repeated number of stacks of the 4 plies. So that makes it very simple. And then, of course, you can taper it, because you can reduce the number of repeats from 10 to 9 to 8, whereas the quad you cannot do that. And in terms of ply drops, the traditional way is to have the ply drops inside the laminate, whereas in the double-double, we can have ply drops in singles now instead of symmetric pairs on the outside. And then the stacking sequence is always a problem with quad, but there's no stacking sequence effects because there are only 2 possible stacking sequences, so the issue goes away. And we can have one-axis layup with no cross-plying, and the interlaminar stresses, when it's homogenized, is the same for all double-double. And then for every laminate, it can be replaced by the double-double. May I have the next slide, please? Here's the difference between a heterogeneous quad laminates on the left versus that are homogenized on the right. As you can see, the difference that as you reduce the thickness in order to save weight, the homogenized double-double remains the same, the constant properties, whereas the quad you cannot. Can I have the next slide, please? And how much weight can you save? You can save substantial weight when you switch from quad to double-double. As you can see, these are percentages of weight you can save, and you have 52%, 63%, 67%, and 52%. And then in terms of the layups, you can have one-axis layup, or you can have uniform thickness. May I have the next slide? Here is an example of how you can do a stringer, and this is reported in the book in the chapter 3. And then you can see you can taper it from the toes, where you have minimum number of plies, 4 plies, up to the thickest section where you need it, which is 8 plies. So it's very easy to do. In particular, this is done by a card sliding. So that is, in terms of layup, is very fast and less prone to error. And in addition, you get the natural taper all on the outside. May I have the next slide, please? So finally, we have a demonstration model with you showing the grid, and we are proposing to use a metallic grid, and this is easy to manufacture using a water jet or fiber wire shaping. And then we take advantage of the negative thermal expansion of the skin in plus or minus 60, so that you can assemble this, chilling both components and put it there together, and without glue and without fasteners. So that the layup could be one-axis layup on the skin, and so that this is done without any complicated tooling, or there's no issue with molding and demolding and so forth. So this is what we propose, and thank you very much for your attention. And we will be around to answer questions. Oh, finally, there's one showing the double-double, and this will be shown in a particular, this is what we call lamination parameters. And this is the domain of the double-double on the left. But you can have additional complications, but you wind up having less regions. So the double-double on the left is the best compromise. Thank you very much for your attention.
Thank you very much, Steve.
Steve will stay online and will be very happy to answer questions at the end.
Could we have the next slide, please? Okay, thank you very much. It's now my pleasure to introduce our third author and speaker today, Naresh Sharma, who's the CEO and founder of an Italian company called Nashero. Naresh Sharma is the CEO and founder of Nashero, an EN 9100 certified light aircraft manufacturer based in North Italy. Since 2008, Naresh is an ASTM member and an active contributor to the ASTM's aviation standards, including those for general aviation, by participation in the F-44, F-39 and F-37 groups or committees, and as well as other committees within the ASTM. Naresh earned a PhD in aerospace engineering and computer sciences from Delft University of Technology in 1997, a master's in aeronautical engineering from the Indian Institute of Technology, IIT, in Kanpur in 1989, and a bachelor's in mechanical engineering from IIT Kanpur in 1986. Naresh, the floor is yours. Thank you.
Thank you, Andrew. So I would just take a couple of seconds to talk about one thing which we missed. Professor Tsaï's contributions have been so enormous in the industry of composites that we have named a modulus in his name, which was an invention that he did, which I would like to make sure that doesn't go unnoticed. He has developed one constant, one simple constant that would be able to define the material characteristics of any composite material. And that is called size modulus. Actually, I would implore all of you to read the previous book, the two previous books in which he has mentioned those. So with that, I'll start my double-double manufacturing and certification. If I can move the next slide. Okay, so in the book, this is based on the book. In the book, we have shown that weight savings of over 45%, means weight savings of over 45% we can get from DD, because this is the only technology available today in the world that can allow you to actually halve the structural mass of a product. that can actually allow you to have the structural mass of a product. And when we talk about products, we talk about wings, we talk about fuselages, we talk about horizontal stabilizers, and we talk about spars and skins and all those things. So if you have weight savings of 45% over a modern Airbus 350, you'd be able to double more than double the range, and you'll be able to save enormous amounts of carbon emissions, more than what we are trying to talk about today. We're talking about carbon emissions being saved by changing the engine, by consuming less and consuming more. Weight saving is the primary cause of, because you are carrying people. So if you have more capacity in your aircraft because you have lost, reduced the mass, that's the biggest weight saving that you can get. And we have shown in the book the amount you can save. And the other thing that I would talk about is the amount of easy stockage of material, because now you don't have to stock many different kinds of, I'm sure that all of you are over here from the composites industry, and you know when you create kitting of an airplane or kitting of a part, kitting means that you cut out pieces which are eventually used by your workers in order to do an assembly on the mold or using the laser or whichever technique you use to accurately make that part. In this case, you'd be using single axis layup. All the layup will be in one axis, and that makes stockage extremely easy. You're stocking the minimum number of materials that you need. High quality surface. So over here in this show, you will see many parts which will be exaggerated with clear coats to disguise the defects on the surface. This part I have made is out of DD. It has not a single, it doesn't have a single gram of paint on it. And I'd keep it over here for any one of you to walk over and take a look at the quality of the surface of this part. This is part of an actual airplane. And so those were the things I wanted to cover, and I've already told you those. So let us go ahead. Now, one of the things that I have brought for you to see is this thing that you see in the hand, in that hand, which is a tapered beam, which Professor Tsaï just talked about. This was actually tested at NIAR, and it went 500,000 cycles. After 500,000 cycles, it was tested for residual strength. It was tested at 500,000 cycles at limit load, and then it was tested for residual strength. And its residual strength was the same as that of a pristine coupon. So we are talking about materials, and we are talking about technologies which allow you to get the maximum that you can out of composite materials. These are some parts that we have. That is an embedded part which on the structure, on the outside, that is the fork of a landing gear of our aircraft. From outside, it has hybrid Kevlar carbon material for crash protection, but inside it is a DD material. And it has embedded hard points. You look at the complexity you can get out of this. So this is what I wanted to talk about. And I will leave these parts over here, and you can take them, and you can take a look at them. These are some coupons that were tested at the laboratory of University of Porto by Professor Albertino, who is going to talk shortly. Thank you. Thank you. Please don't take these parts away. You can look at them, but leave them.
Okay. Thank you, Naresh. It's now my pleasure to introduce our next and final speaker, Albertino ARTEIRO, who is assistant professor at the University of Porto. He is assistant professor at the Materials and Technological Process Group of the Department of Mechanical Engineering. which is part of the Faculty of Engineering at the University of Porto, which is abbreviated FEUP. He received a master's degree from FEUP in mechanical engineering in 2012 and a doctoral degree in mechanical engineering cum laude from the same university in 2016, during which he was a visiting student researcher at the Department of Aeronautics and Astronautics of Standford University. His research interests include composite materials modeling at different length scales, design and analysis of composite systems based on new concepts, and composites manufacturing. Albertino, the floor is yours.
Okay, thank you for the introduction. So the topic that I bring today is actually titled there as optimal double-double laminate search and toughness, although for this presentation I'll be essentially focusing on the notched response of this new family of laminates. Nevertheless, let me start by saying that for me it was not a surprise to see this early afternoon that, for example, ARTEIRO, they are considering double-double as the basic building block for their topology optimization tools. And that's really because of the flexibility that DD brings in terms of optimal design. Now, going to my focus today, so that's on the notched response of double-double laminates. And regarding the motivation for this, I think this is pretty much clear. So structural components, they need to be designed taking into account the effect of stress concentrations, which may arise due to geometrical discontinuities like windows or excess holes or holes for mechanical joints, but also from in-service damage, like, for example, when it comes to the penetration by a foreign object in the fuselage, okay, for an open rotor aircraft, for example. If we plan to integrate double-double in this type of, or towards this type of applications, and in terms of designing with these laminates and obtaining their design allowables, for example, this is not different from what you would do with quad or legacy laminates, or it actually can even become simpler. So what I'm going to show you here is just a summary of some of the test data that is published in the previous and in the current book. So these are specimens manufactured from non-cream fabric C-ply by resin infusion by Naresh in his company, Nashero, using the same NCF building block in this particular case, so that's a 050 NCF, which you can, for example, laminate it as a 00 plus minus 50, or as a 1565 minus 65. Although, I mean, you can choose whatever is optimal to your design. So what I'm showing here is the stress, the remote stress strain curve for the unnotched case, and then we also tested, So we also tested open-hole laminates, and what you see here is, so on the left, for the whole diameter equal to 0, so that those are the unnotched strength from the previous slide, and then you see two or a few tests on two geometries with an open hole, where you see this common notch size effect. And what you see, so you see in full the mean values from those tests, and in the open bullets you can see the B values. So this is not, as I was saying, different from what you do with other materials. Now the question is, what type of flexibility then could double-double bring in terms of designing, for example, for notched strength of composite laminates? To do this exercise, I take an analytical tool that has been applied and fully validated for notch tension and compression strength prediction of legacy laminates, and we'll be applying these in the context of double-double. So, as I said, it's a closed-form solution based on a theory called finite fracture mechanics. Essentially, you have to solve a system of equations where you have in the first line a stress equilibrium in the sense of an average stress criterion, and in the second line you have an energy balance in the context of finite fracture mechanics, okay, or fracture mechanics in general. So to solve the left-hand side of both equations, you just need the stress distributions around the hole and the stress intensity factor distributions for different crack length. These are some things, or these are things that you can get either from analytical solutions or from calibration in a finite element model if the laminate is too orthotropic. And on the right, what you have are the material properties, so the required ingredients to solve the system of equations. Okay, so you have the laminate strength in the top, and you have the laminate fracture toughness in the bottom. Using other analytical technologies, including size modulus or the trace of the in-plane stiffness matrix, as Naresh was saying earlier, you can actually derive the laminate or the strength and the fracture toughness of any laminate using the ply strength and the ply fracture toughness. Okay, so you just need the strength of a unidirectional 0-degree ply and its fracture toughness as well, and then with size modulus you can actually derive those properties, and you can do that for legacy quad laminates, and you can also do it for double-double. So let's see then how I'll do the predictions come out. So these are the experimental results that I've just shown 2 slides ago, and if we apply the finite fracture mechanics criteria to predict the notched strength or the notch size effect, you can see that they just match, they just overlap the predictions. Okay, so since you're bringing the physics into the problem in terms of stress equilibrium and energy equilibrium, so you're considering both of them, then you can really predict with a very good level of accuracy the notched strength of any laminate, including double-double, using only the strength, the fracture toughness of the 0-degree ply and size modulus. Okay? Now, what is the exercise then that we can do? Just let's take different phi angles for the first angle ply, and then you can vary the psi angle for the second for the second double. And what I'm plotting there is essentially the band for the notched strength of those laminates on an open hole specimen with a hole diameter of 6 millimeters and a width to hole diameter ratio of 6. And you can see how the predictions come out. And the question that you can make then is, how would this compare with the notched strength of quad laminates, for example? I did the same exercise. Unfortunately, the colors probably don't show very well. But so what you see now on the right is the same exercise, but considering the typical way of discretizing legacy quad laminates, so in terms of percentage of 0-degree plies, 90-degree plies, plus minus 45-degree plies, and you can see that in terms of notched response, you can actually match the notched strength of quad laminates with double-double laminates. Nevertheless, I should call your attention for the fact that although the plots on the right are continuous, remember that quad are not continuous. So actually, many of the solutions that you see there on the right are unfeasible from a layup or lamination point of view, whereas the ones on the left, all of them are feasible. Okay? In addition to this, if we pay attention to some of the curves on the left, we can even define other interesting concepts that can make certification rather easier, like, for example, the concept of target laminates, because you can actually see that for some particular angle plies, there is almost no variation of the notched strength, or in other words, the notched strength is almost insensitive to the angle ply, or to the double ply angle. Okay, which means that if you want to derive the design allowables for your structure, you can probably select one of these target laminates, because in terms of confidence of the data that you'll be getting, you are 100% sure of what you obtain, independently of the manufacturing technology that you're using. So to conclude, saying that novel analysis techniques cannot be effectively exploited using decades-old design concepts, and this refers to the particular case of quad laminates. So you see that, those are the lamination parameters space. You can see that it's not a full space, so that there are unfeasible regions, whereas with double-double, you always have feasible regions everywhere. Composite structures can become more affordable and competitive with this type of technology, for example, using the target laminates. The new possibilities for more efficient design and certification are endless, and embracing such philosophy can lead to the next game changer of this industry. Thank you.
So I'd just like to show two slides of conclusion before we wrap up and get the session back. So if you want to start double-double, now you know what it is. What can you do? You need to get the book. It will be soon available. Don't worry, you can get an e-book if you want. You can get all the software to design double-double, and that's free from our website, either Standford or Think Composite website. Of course, you will, at the two websites, you can get them. You can download them, it's free. Of course, you will, if you need it, you can get free online, get started training, and that's also free from either Think Composite or for Standford. And finally, if you want to go into deep knowledge of double-double, we advise you to go to the next composite design workshop, the 23rd one, which will be it's a 5 days online course by Standford, and you see here also the website to register. So I'd like to conclude just to tell you that we think that double-double is a really enabling technology for sustainable, lighter, cost-efficient, faster manufactured composite laminates. If you want more discussion during the trade show, you may come to the SHARMA booth, SHARMA Innovation. All 5 stand G42 will be there. The structure also will be there. So you can see them and talk with me, Naresh. We'll all be there, and we'll be happy to answer all your questions, even now. Steve is online, so if you have good question for him, he will be happy to answer. Thank you so much. Steve, are you online? Is there any question in the room?
Oh, thank you very much. Edgar Foos from GKN Aerospace. First, I wanted to say what an honor it is to hear from Steve Tsaï. I studied your failure criteria when I was growing up in university, and it's great to put a face to the name, and it's just an honor to have heard from you today. So my question is we've heard a lot about the benefits, but could you maybe explain how impact damage or delamination would be affected by a double-double laminate?
Have you Steve online? Steve, are you online? If not, maybe one of us can answer. Impact. Impact.
Can you please repeat the question once again?
Sure. You talked a lot about the mechanical properties in terms of the strength and the benefits you get from a double-double laminate, but how does that laminate work for impact damage? Would I expect it to be better to withstand impact damage from a particular given energy of impact? Would I be concerned about delaminations in such a laminate that are different from a standard quad layup, for example? So just describe a bit about impact damage on a double-double laminate.
So that's an excellent question, and I wanted to actually make a point when Albertino just finished. Everybody talks about impact damage requires off-axis plies, right? It is always said that you would require 90-degree plies, and that would reduce, that would increase the impact damage strength. But as Albertino's presentation, he showed that he has the theory that they have used and the experiments that they have performed in order to validate their theory prove that the behavior of double-double is at least as good as an equivalent legacy quad laminate, even though you would not be able to produce a legacy quad laminate, but should there have been a legacy quad laminate of that type, it would have almost almost the same or less impact damage strength, because that comes from the open notched strength. The other thing I'd like to say is that people always confused with the double-double laminates, that they do not have enough, that they have less impact damage because of the angles. The impact strength actually comes from homogenization, and there is no other technology that will give you a homogenized laminate than Professor Tsaï. And I'll give to him because I think he'll be able to talk about impact strength.
Yeah, so regarding the impact response of this type of laminates, I guess, unfortunately, we were not able to test yet this type of laminates under that specific loading scenario. What I can say from my experience, and precisely in line with what Naresh was saying, is that the main concept within double-double is homogenization. And so, in principle, you'll be reducing the sensitivity to the appearance of interlaminar damage, even when considering low velocity impact. Okay? Now, the consequence is that eventually the impact response may indeed change, as you were suggesting. I'm not sure whether the change will come from the extent or the type of delamination that you get, but you may indeed get different failure modes. So it's something that you do need to characterize. Going back again to my experience, I have been working for many years on thin ply laminates, where you can essentially get those homogenized building blocks even with quad, and that's exactly what we observe. So the impact response tends to go from a delamination type of damage to fiber failure, and these will of course have consequences on the residual strength of your laminate. Whether it is better or not, then it really depends from case to case.
Are you from GKN Aerospace? So I would give you a proposal. We will ship you for free a laminate made from double-double, and you do testing of in your premises of impact damage. You can do a drop test, or you can do whichever test you want, or an ASTM test, and then you look for yourself and you report to us at the next JEC.
So I just want to add also that we are now doing that type of testing at the University of Southern California. Bojin is doing it, and hopefully we'll get some nice results, and they will be all inside the book, probably the second edition that should come in July or something. So we hope to have a result and really answer your question, and we can check against yours. Any other question? Yes?
Well, thanks for your talk. This is simple twofold symmetry. Has there been a study for threefold rotational symmetry instead of using a four symmetry axis for this whole study? You could then use not half of the material, but a third or 2/3 of the material. Is that something that has even been considered?
So basically, you'd understand where the symmetry comes from, right? We have the LAM search expert over there, and he will tell you that basically, if you have two axes and you split each axis in two, right? That's what we're doing. You split each axis in two. You'd be able to cover the entire bandwidth of the stiffness requirements that a laminate has. And that's what has been done. Since, I don't understand how would 3-axis benefit from that, because 2-axis covers the entire, the entire bandwidth. If you look at our plots, we have the cover of the book, that image, we can show that image if possible. That'll show you the bandwidth we can bring to bear. But your question is valid so long as we can, if you show that we cannot model the thing that we do using 2 axes, we would go for 3, but that's not necessary. We have done a single axis, a single double, that is just 2 angles, one plus minus phi angle, which would be considered to be, in your concept, a single axis, right? We have done that for application, and I'm not allowed to say which application it is, but it's for a space going rocket, and it was for a loading structure. And that was a single axis laminate that actually resolved all the things. So in that case, our phi was non-existent. Only one double was used, because the loading was very, very uniform and regular.
Question? Yes. You can come to SHARMA. We can have I will show you on the software how we can show the space where we work. Good. Thank you. Thank you for your question. Any other questions in the floor? Yeah. Question? No? No question? So thank you very much. We're very happy to have you here so late in the afternoon, and thank you so much for being here.